Hi everyone, we'll get started shortly with the lesson today. I'm just going to wait for some more people to come in. Probably get started at about 6:03, 6:04. Just a reminder, so we'll probably get started at about 6:05. It shouldn't be too difficult today. So today the plan is basically to go over amount of substance and some basic mathematical chemistry, followed by hopefully some time to do some example questions. And hopefully also some time to answer your questions. It should be about an hour, but it probably will take about 45 minutes today's lesson. So just to let you know, I'll try and go a bit slowly for it as well. Amount of substance, so moles, Avogadro's constant, relative atomic mass, basically all the basic mathematics you need to know for chemistry. Approaching potentially, I think we'll also talk about titration equations, titration calculations, how to best approach those. So it's basically calculation chemistry. Start in about 5 minutes. And that about 4 minutes. Recording of this lesson will be posted onto YouTube, onto the StudyMind YouTube channel. So you should be able to get access to that. Right, guys, let's get started. Let's jump right into it today. So, a relative atomic mass and relative molecular mass. So we're going to start with some basic definitions. It's really important to understand what each of these terms mean before we can start building on it with calculations. I should turn my lights on. I've got a lamp in the background, so hopefully that's okay. Okay, so starting with definitions. So relative atomic mass. So the relative atomic mass is the average mass of an atom of an element compared to 1/12 the mass of an atom of carbon-12. So basically, what you've got is what you're doing is you're weighing this element and what you're comparing it to, because remember, you can't just weigh the mass of an element. It would be so tiny that it would be a bit pointless to weigh it. So what you're comparing it to is you're comparing it to how much does that element weigh comparative to 1/12 the mass of an atom of carbon-12. And carbon is used as the standard by which all other elements are compared. And carbon has a relative atomic mass of 12. So 1/12 of that is a relative atomic mass of 1. And 1 belongs to hydrogen. The relative atomic mass can be found on a periodic table by looking at the bigger number above the element symbol. Now, it could be, so it is normally above, but in some of the older periodic tables, you'll spot that it will be below. And it does depend on the country, and it does depend on the structure. So the relative atomic mass is the bigger number on the periodic table. That's important to note. Relative molecular mass is the average mass of a molecule relative to 1/12 the mass of an atom of carbon-12. So what you've done here is, rather than having the mass of an element, of an atom of an element, you have the mass of you have the mass of all of the elements that form together, to join together to make this molecule. And 1/12 of that is the relative molecular mass. So for nitrogen, N2, chlorine, Cl2, O2, those are all molecules. Relative isotopic mass is the relative mass of an atom of an isotope relative to 1/12 the mass of an atom of carbon-12. So really important to note that. So isotopes are different forms of atoms with the same proton number, but a different number for a different mass number, because they have a different number of neutrons. So they share similar chemical properties, but they have different physical properties. So their mass and their weight and their density will be different, but their reactivities will be fairly similar, because that's determined by electron number, and electron number stays constant in isotopes. So relative isotopic mass is the mass of an atom of an element relative to 1/12 of the mass of an atom of carbon-12. So relative formula mass now is the last one. So the relative formula mass, or RFM, is the sum of the relative atomic masses of atoms in a formula unit of a compound. So for example, if you have magnesium hydroxide, MgOH2, so Mg has a relative atomic mass of 24.5. Oxygen is 16, hydrogen is 1, but remember you have 2 of those, so you have times 2. So you have 24.5 plus 16 plus 1 times 2, so that's 17 times 2, which is 34. 24.5 plus 34 is 58.5, and that's your relative formula mass of magnesium hydroxide. The difference between relative formula mass and MR, and it's really important to note that. So relative formula mass applies to compounds, relative molecular mass applies to molecules. And the difference between them is molecules are groups of the same element joined together, whereas compounds are groups of different elements joined together. And relative atomic mass is not usually written as a whole number due to the fact that it is the average mass of many, many different isotopes. However, relative isotopic mass will normally be written as a whole number. The best way to calculate relative atomic mass is you multiply the relative isotopic abundance by the mass of each isotope and then add them to each other, divide by 100 and do a sense check. So I'll talk you through this one. I think there is a second one for you guys to have a go at. So this one is it's the relative, it's the mass times by the abundance plus the mass of the second isotope times by the abundance divided by 100. Now, Another way you could do this, and probably a quicker way, is rather than doing the abundance as a percentage, do it as a decimal. If you do this as a decimal with it already divided by 100, this then becomes easier. You don't have to do it as a 3-step process. 35 times 0.75 is, so quickly do this on a calculator because you do have access to a calculator in your exams. 35 times 0.75 is 26.25. 37 times 0.25 is 9.25. You add them together, you get 35.5. And then that represents the relative atomic mass of chlorine. Or a fraction might be easier, says Hannon. I would not agree. I don't think a fraction would tend to be easier. Generally, fractions might be a little bit more complicated to work with. It is generally easier to use it as a decimal form because, again, you don't have to do any division afterwards. The divisions are already done for you. And 35.5, yeah. So divide by 100 and do a sense check. So to calculate the relative molecular mass or the relative formula mass, all you do is you add up the AR of each atom within the molecule. So this should be pretty easy for all of you here. What's the relative molecular mass of water? Should be very easy if you guys put it in the chat. Yeah, I'm getting a lot of answers. This should be very simple. It is 18. Well done. So relative molecular mass of water is 18. So what you've done is you work out the formula, H2O, and then you add up the different atomic, relative atomic masses, add them up, and you get 18. Okay, that shouldn't have been too difficult. We're going to get into slightly more complex chemistry or slightly more complex amount of substance work, the mole and Avogadro's constant. So the mole, what is the mole? A mole is a unit used to measure the amount of substance. It's often written as mole in shorthand form, but what actually is a mole? It's a standardized unit. The idea is the mole represents a weight, and every element or every molecule, every compound has different weights for a mole. But the mole is constant. The number of particles in a mole is constant. 1 mole will always contain 6.02 times 10 to the 23 particles. The weight of those particles might be different, and that would depend on the density and the actual weight of the particle itself. And that depends on the number of protons, the number of neutrons, and the number of electrons that form that particle. But the number of particles within a mole always stays the same. It's always 6.02 times 10 to the 23 particles. So if you look at 1 mole of hydrogen atoms, that's 6.02 times 10 to the 23. 1 mole of water molecules, that's 6.02 times 10 to the 23. 1 mole of potassium ions should be 6.02 times 10 to the 23 ions. Very important to note, if they ask you the number of molecules or the number of particles in the number of hydrogen atoms in 1 mole of water, that would be an Avogadro's constant times 2, because for every mole of water molecules, there's going to be 2 hydrogen atoms, which means that the number of hydrogen atoms will be times 2 in 1 mole of water. And every particle, a particle can be a varied range of things. It can be electrons, atoms, molecules, ions. It can be anything, basically. And the number of particles equals the number of moles times Avogadro's constant. So we've got a question from Sirat here. How do we know when to use the Avogadro's constant to get our answer and when to not use the Avogadro's constant to get your answers? Well, it depends on what the question is asking you for. If the question is giving you a mass, and is asking you to calculate the number of moles, you wouldn't need the Avogadro's constant for that. But if the question has given you a number of particles and is asking you to calculate the number of moles, then you would. Anything where the word particles is mentioned, you're thinking Avogadro's constant needs to be used here. 6.0, Simran, I thought it was 6.022 times 10 to the 23. Yeah, it is 6.022. It's even more than that. It's 6.02273. There's a lot more numbers to it. So you've got to be, it's just basically rounded, and it's rounded to 3 significant figures, which is what you normally give every answer or every value to in chemistry. Everything is given to 3 significant figures. And so you do the same here. So let's have a go at this question together. How many atoms are present in 0.34 moles of sodium metal? So atoms present in 0.34 moles. So you've been asked about particles, and you've been given number of moles. So particles equals moles times Avogadro's constant. So what you do is you do 0.34 times 6.02 times 10 to the power 3. And you get 2.046, this is 2.047 times 10 to the 23 particles. And that's your answer. Easy. Simple as. You don't need to memorize the value for AQA anyway. For other examples, you will. If you have one of the Casio FX calculators, it is actually one of the constants that is referenced in the calculator itself. So if you go into function, you go into constant, so CONT, it's at the bottom, and you click on that, you go into nuclear chemical, Avogadro's constant, or AV, is on there. So if you have the Casio, like the mathematics calculators, the ones that you'll use for math, that value is programmed onto that. The mass of 1 mole of a substance is the same as the relative molecular mass of the substance in grams. So if the MR of CO2 is 44, 1 mole of CO2 will have a mass of 44 grams. That's why we use carbon as the standard, because carbon, 1/12 of a carbon atom is 1 gram, basically. 1 mole of it is 1 gram. So therefore, the number of moles is equal to the mass of a substance divided by the MR. This is a question, a very common calculation you need to be able to do, and you need to be able to do very quickly in your mind. Have a go at this one, everyone. So this shouldn't be too difficult. See, any answers? Put your answers in the chat. 88 grams, 88 grams, 88 grams, 88, 88. Yeah. And so we're seeing lots and lots of 88 grams. Well done. Because mass of a substance is the number of moles times by the MR. There are 2 moles. The MR is 44, which means it's 88 grams. Concentration. So the concentration of a solution is equal to is defined as the number of moles that are dissolved in 1 decimeter cubed of a solution. 1 decimeter cubed is equal to a liter, but basically the concentration isn't necessarily the number of moles, but for the sake of simplicity, we're calling it that. Remember, your concentration can be anything. It can be in mass. It's basically amount of substance dissolved in 1 decimeter cubed of a solution. And that's really important. It's a really important distinction to make, that it's not only the number of moles, because when you get to A2 calculations, often they might actually give you in grams per decimeter cube, and you'll be expected to work backwards for some of the more complex titration questions. Mole per decimeter cubed is the number of units used, is the unit used to measure the concentration of a solution. And the concentration overall broadly is defined as the number of moles per unit volume. And that's really important to note. So number of moles equals concentration times volume. Concentration times volume equals number of moles, N equals CV. Really important to know that. So let's do this together, because this one is a complex, more complex question. So 25 centimeters is equal to 0.025 decimeter cubed is the volume, and the concentration equals 1.5 mole per dm. So N, the number of moles, was 0.0375 moles. But that's not the amount of the substance. That's not the mass of the substance. To work back, what you have to do is N times MR gives you mass. So what's the MR of calcium carbonate? So calcium is 40. It's 40.1, but for the sake of simplicity, we're going to go with 40. So 40 plus 12 plus 48, which is 52 plus 48, which is 100. So times that by 100 equals 3.75 grams. Do we follow? Does that make sense? Does that make sense how I got that? Everyone kind of comfortable? Happy? Cool. Good. Yeah. And that's something that you do need to be very familiar with. Okay, the next equation is the ideal gas equation. And this is really important to note. So the ideal gas equation, PV equals nRT. The really important thing to note for this one is the units, because the units are often the thing that catches students out. So because the units aren't standard SI units, it becomes a little bit more difficult. You should be able to use the ideal gas equation in calculations. You won't be expected to recall the value of the gas constant, 8.314, for those who are able to recall it. So the ideal gas equation is used to calculate the number of moles of a span in a specific volume of gas. Now, in GCSE and before, you'll have worked with the assumption that N equals mass over 24. And the reason you would have done 24 is because you know that a standard gas at room temperature and pressure occupies a volume. 1 mole of a standard gas at room temperature and pressure will occupy a volume of 24 decimeter cubed. The problem is that in real chemistry, we don't use 24 decimeter cubed isn't everywhere. We're not working under ideal circumstances. We're not working under the assumption that things are working perfectly. So the ideal gas equation helps us adjust that to the circumstances that we have in our actual calculation. PV equals nRT. So it's really important to note this. So pressure is given in pascals, not kilopascals, which is what the unit that you'll often be seen it given as. Volume is in meters cubed, not decimeter cubed. Number of moles, number of moles. Temperature is in Kelvin, not degrees C. Converting, important to note. So converting from kilopascals to pascals, you multiply by 1,000. converting from decimeter cubed to meter cubed, divide by 1,000. Some of you in the audience, smart people, may have noticed that actually these two cancel each other out, which means if you are given an equation in decimeter cubed and in kilopascals, you can leave it like that because they balance each other out. But if you're converting one, you have to convert the other. The last equation, Kelvin, so temperature plus 293. Sorry, not 293, plus 273 is to convert from degree C to Kelvin. And it's important to note those unit equations. And you need to be able to do those from your standard equations. Apart from that, there isn't anything more to that equation. It's just to put it all into practice. So let's do this together. So 20 degrees Celsius in Kelvin. So you add 273. So you get 293. 800 centimeters in meters cubed, difficult. That's 0.8 decimeters, which means it's 0.0008 meters cubed. 5 decimeters in meters cubed. So 5 divided by 1,000 is 0.005. 100,000, yeah. 0.5 kilopascals in pascals, 500 pascals. Easy, because you times by 1,000. Okay. Let's do this one together. Okay. A gas occupies, so I'm just going to put the unit at the top, and we've been asked to work out the relative molecular mass of this gas, which actually means that we're going to have to work out moles. So PV over RT equals N. You've been given the, you know R is 8.314. And you know T is 45 degrees Celsius plus 273 will be 308 degrees Kelvin. Pretty sure 318 degrees Kelvin. Sorry, mistake on my part. You've been given this in centimeters and in kilopascals, so you have to convert. Centimeters to decimeters is centimeters divided by 1,000, so 1.25 dm. 1.2. Actually, what I'm going to do is, for the sake of simplicity, I'm just going to keep it in decimeters and in kilopascals. Again, doesn't really matter. So, important rule here. Rule. Due to the calculation conversions, E and V can either be in kPa or and dm to the -3, or in pascals and meters. It doesn't really matter. It just follow what you're given. And this is an important rule, and I'm going to leave it on here just for you guys to understand that. So now I'm working with this. So let me get my calculator out because I'm not that good at maths. Not that good at mental maths anyway. So you've got 131.25 at the top. And at the bottom, you've got 2,643.852. Now you just do the calculation, 131.25 divided by 2,643.852, and you basically get 0.0496 moles. but you've been asked to work out the relative molecular mass. So mass divided by moles equals MR. You've been given a mass of 2.4. And you've been given a relative mass of about 52.6. And that's how you use the PV equals nRT equation to basically work out different molecules. Okay, I'm going to take a quick break here. Just, I'm going to put a message in the chat. If you can give us a review for this lesson, and if you've attended some of the other lessons, just for a moment, if you're able to sort of give us a quick, it'll take 2 minutes. I'll stop for 2 minutes just to let you kind of have a moment to write that. And then we'll move on to some more content and some exam questions after that. But if you are able to, it would be a huge help, and it would be great feedback for us just to know kind of what we're doing okay, what we're doing, what we can work on. Which other slide? Sorry, give me a sec. No question. Cool. If you are able to write it down, let me know once you're done. Once you finish writing your review, I will get back to the class as well. Give another minute, just so that you have the opportunity to write a review. 48, but I think you keep getting 48. Yeah, it probably would be. Oh, let me double check. Let me put it back into my calculator. Might just be a typo. Double check. Okay, so let's do it in my way. It probably is a rounding issue, because I have rounded earlier, but I think it will be 48. If people are saying 48, let's give it a second go. Might as well. Let's see where we're at. It probably is just my fault. 1.25 times 8, no, not times 8.31, times 105 divided by 8.31 times 380. So that's the answer for the number of moles. Let me double check how. The problem is I don't have a scientific calculator on me. So, I can try them with brackets. Okay, so they've gone for 8.31 rather than 8.314. So the number of moles I still get out to 0.04966673705. The problem is I can't store that, but calculator. And then I would just do 2.4 divided by 0.0496. Yeah, so this time I got it to 48.4. So it probably was just a mistake. Yeah, it probably was just a simple, I think maybe I had accidentally written 0.0469 rather than 496 down when I was doing it earlier. Yeah, because if I do 469, it gets me to 52. It probably was just a mistake. Sorry, guys, that's on me. Cool. Everyone else comfortable? Right. Time to carry on. Empirical and molecular formulae. So you need to be able to define these terms, empirical and molecular formula. So empirical formula. So let's start with molecular. Molecular formula is the actual number of atoms of each element present in a compound. So this is the literal. This is what this compound is made up of. The empirical formulae, however, is some of these compounds can be very complex. So what we're going to do is we're going to try and simplify that. And we're going to simplify it into a ratio to show the relative amount of each element that's present in the compound. The empirical mass is the mass of all of the atoms present in the empirical formulae. Okay, so relationship, a certain number of empirical units are going to make up the molecular formulae. So it tells you the ratio times by something is going to give you the actual number of each of these. So let's say you've got here the empirical unit, or the amount that if you do HO multiplied by something equals H2O2, that something is just going to be 2, so that you have 2 of each hydrogen and 2 of each oxygen. So that's the way to simplify that. So this, let's play H2O. So the simplest formulae is just H2O, the empirical formulae for this one. Because remember, it has to be whole number. CH2O, as you can see, because if you times that by 6, it gives you all the same numbers. HO, C2H5, because if you multiply that by 2, you get C4H10. But if you divide that by 2, you can get a whole number. And CH for benzene, because again, if you times that by 6, you get the full number. You get the full molecular formula. So let's find out how to calculate molecular formulae and empirical formulae. So the first thing you do, when you get a question like this, the first thing I'm doing is I'm going to highlight everything that's important information for me. So empirical formulae, relative molecular mass of 180. What's its molecular formula? Now, I have the empirical formula. Something will give me a molecular formula, which is N. I don't know what this something is first. So the first thing I want to do is I want to find out what that something is. So the best way to do this is to work out the empirical mass. So the empirical mass is 12 plus 2 plus 16, which is 14 plus 16, which is 30. Then I want to find out the ratio or the scale factor between the empirical mass and the actual and the molecular mass. And that's 6, which means that this empirical unit is 6, which now means that my structure is glucose and the molecular formula is C6H12O6. Molecule is therefore glucose. So all you do is you work out the empirical mass, you work out the molecular mass to the empirical mass ratio, and then you divide and you move back upwards. Students should also be able to calculate empirical formulae from data giving composition by mass. So this is slightly more difficult. So the way to do this is basically, you want to find out the ratio of these elements relative to their mass, but you want to get rid of the bit that says the mass is actually changing this. So the first thing you do is you put this as a ratio of its percentages. You know that these percentages will total 100, and the first thing you do is divide them all by their ARs. So get a calculator. Divide by 12, so 5.4. And so now you've been given what you've got is you've got their ratios without them not relative to the masses, which is really important because now these ratios are not relative to anything. The next thing you want to do is now you want to get this into a whole number format. And so the best way to do this is to divide all of these by the smallest of the percentages that you've got. So divide all of these by 1.35. And what that'll give you is that'll give you their whole number ratios, or at least a fraction of their whole numbers ratios. So you know the oxygen is 1. 2.62 divided by 1.35. This is about 10. It's approximately 10. It's 10.1, but we can round because you know there'll be some rounding errors anyway. And this is exactly 4. So now I'll put this together, C4. And it's likely to be butanol. And that's likely to be the formula. Okay. So you calculate the number of moles, and then you divide by the number of moles of each element by the lowest number of moles, and you work backwards. Okay. Let's have a go at this one. This is slightly more challenging. I'm going to let you guys have a go at this. I'm going to give you 2 minutes before, and then I'm going to ask you to put your answers in the chat. I'm giving you 2 minutes to just work on it, and then I'll ask you to put your answers in the chat. Okay, if people are comfortable to write their answers in the chat. CH4, so we've got the CH2 or CH4, CH4. CH2, okay, so there's a bit of controversy in the answers. Let's find out. So 4.4 grams of CO2 are produced and 3.6 grams of O2 are produced. And we know it's a hydrocarbon, so it only contains hydrogen and carbon. So the best way to do this is basically, we know that this 4.4 grams contains carbon. So it's CH4. I'll explain why. So the MR of CO2, so we need to calculate the number of moles of each of the products, CO2 and H2O. So 44, 18. So 4.4 divided by 44 gives you 0.1 moles of CO2. And number of moles of H2O is 3.6 divided by 18, which is 0.2 moles of H2O. But what has got you, and what has got most students here, is they've not recognized that this is the number of moles of H2O as a molecule. But for every 1 mole of H2O, there are 2 moles of hydrogen by itself, because there is H2. There's 2 hydrogens for every oxygen in H2O. So what you have to do is you have to recognize that this is 0.2 times 2, which is 0.4. Now the ratio of 0.1 to 0.4, because now you've already got the moles, you divide both of them by 0.1, which then means that it's a 1:4 ratio, which is CH4. Well done. Right, last thing we're going to talk about quickly is balancing equations. We're just going to discuss these quite quickly. We're not going to go into too much depth on them. We will talk about balancing equations, percentage yield, and hopefully, if we have time, atom economy. But I'm actually going to skip a little bit of this. I think balancing equations is something you should be quite familiar with. Let me know if anyone does struggle with balancing equations, put it in the chat. But I think balancing equations is something that you should be fairly comfortable with by this point, which is why I'm not really going to talk about this that much. I'm going to mainly focus on percentage yield and atom economy because that's in the scope of today's lesson. Okay. So, calculating masses from balanced equations. So what mass of magnesium oxide is produced when 12 grams of magnesium is completely combusted in air? So the first thing you want to do is you want to draw out an equation. So write out a balanced equation for this. So magnesium plus oxygen gives you magnesium oxide, and it's balanced to 2:1. You work out the relative MR and AR of the substances. So magnesium is 24.3 and magnesium oxide is 40.3. Work out the number of moles of magnesium that reacts in this equation, which is 12 divided by 24.3, gives you 0.494 moles. And you know it's a 2:2 ratio, which is a 1:1 ratio, which means that you're producing 0.494 moles of MgO. Now, you've been given the moles, you've got the MR, work backwards. So moles times MR gives you the number of the amount of substance produced, and it's 20.15. That's kind of it to work out masses. But let's talk about, volume. Actually, we won't talk about this too much, because again, this is ideal gas stuff. Percentage yields and atom economy. This is more important. So percentage yield, what is that? What is the theoretical yield? The theoretical yield is the quantity of a product that should be obtained in a reaction if the reaction goes to completion. We're assuming that this is a closed system, so there's no transfer of chemicals to or from the reaction. The actual yield is there's always going to be some form of waste. And the actual yield is the amount of product that is obtained in reality in the reaction. And this is always going to be smaller than your theoretical yield. For example, if we had 200 milliliters of milk and 50 mils of espresso coffee, you combine them and you blend the mixture before pouring the drink into a glass, you would expect that you're going to produce 250 mil, but actually you're going to produce slightly less than that, because remember, as you're blending it, some of the yield is going to disappear. Some of the product could be lost. Some of the reactants might just not react. Other products could be made. So there could be other reasons why this doesn't work. The actual yield divided by the theoretical yield times by 100 is the percentage yield calculation. So let's do this one. Methanol, ethanoic acid. He reacts 5 grams of methanol with excess acid, measures the methanoic acid methylethanoate produced, percentage yield of this equation. AR values as followed. So you've been given the theoretical yield. So the actual yield. You've been given the actual yield. It's 9.6 grams. You want to work out the theoretical yield. So methanol, CH3OH, plus ethanoic acid, CH3COOH, gives you methylethanoate, CH3 CH3 plus H2O. And for every mole you're producing, you're producing 1 mole of water. So it's a 1-to-1 equation. So work out the moles of methanol you've used. So 12 plus 2 plus 16 plus 1. So 12 plus 3 plus 16 is 31. 5 over 31 is your moles of CH3OH, which let's quickly put into a calculator. Is about 0.1613. And you know it's a 1-to-1 reaction, so you're producing this much of CH3COOH, the methylethanoate. So you've got this, multiply this moles by the MR of, so 12 plus 3 is 15, plus 15, plus 12, plus 16, plus 16. Got a question here. Isn't it 32? Because 12 plus 16. Why would it be 12 plus 3 plus? Isn't it? It's CH. You're right. 32. So that slightly changes it. 5 over 32, which is 0.15625. And then multiply that by CH3 by 12 plus 3 plus 16 plus 16 plus 12 plus 12 plus 3. And you get a theoretical yield of 11.56 grams. So 9.6 divided by 11.56 times by 100. And so divide the actual yield by the theoretical yield times by 100, and you get a percentage yield of about 83%. Does that kind of make sense? Yeah, fine. What I will do is, rather than repeating how to do this question, what I'm going to do is I'm going to give you a process to doing this. So 1, identify what they've given you, what they have told you. So they will either give you an actual yield or a theoretical. 2, calculate the moles of the reactant. Oh, no. Now, step 2 is write a balanced equation. Step 3 is calculate the number of moles reactant used. And that usually is done by mass over MR. 4, calculate the number of moles. You don't have to write state symbols. Remember, this is just for your working. It's not going to get marked anyway. But in a normal balanced equation, yes, you would write state symbols. Of product produced. So this is your actual yield. No, this is your theoretical. And the way you do this, theoretical moles, and the way you do this is you look at the ratio of moles of reactant to product. 5, work backwards and calculate the theoretical mass. Again, you're doing this by doing N times MR. And then 6, calculate percentage yield, which is actual divided by theoretical times by 100. And that's your six-step process to calculating percentage yield. Okay. I'm going to give you a second to write that down, and then I'm going to actually wrap up. I'm going to do a quick summary, and just wrap up. But yeah, 82.8%. Okay. Right. Got a question here in the chat from someone. Are they recorded? Yeah, they're recorded. They're being posted to YouTube right now. So if you basically find out if you look at the Study Mind YouTube link, you should be able to access these recordings after the lesson is finished. So you can have some time to go through the questions. Right, summary. So today we've done quite a lot. We've talked about relative atomic mass. We've defined our key terms. We talked about the mole, Avogadro's constant, both the molar equations for mass and the molar equations for concentration. We've done the ideal gas equation, and we ended with empirical molecular formulae, and we've also had some time to go over percentage yield. We haven't done atom economy today, unfortunately, and I will try and record a video for you guys for atom economy and post it to the YouTube so you can take a look at that. But we might, and if we have time, we might be able to go through it in a later lesson. But do you have any questions? Could we be sent the PowerPoint? I don't think we'll be sending out PowerPoints, unfortunately. Questions about biology books or websites on non-Hodgkin's lymphoma that go in depth. YouTube videos, there are some really good ones. Osmosis does quite well for Hodgkin's lymphoma. It starts with the basics and it builds you up. It will tell you about the map pathophys and the treatments and stuff. Yeah, that would be my suggestion. Right. I'm going to wrap this up. Thank you all.